Okay, let's play with the proof checker. If you've already been doing it, there may be parts of this video that you can skip. You'll know them when you see them. And if you have not used the proof checker yet, let's do it together. Okay, step number one. Let's start by trying to do something we know we shouldn't be able to do, just to see what happens. So we've already said we don't want to be able to prove this kind of argument. It does not follow from the fact that one person has a property that everyone does. For example, Tanya wears glasses, so everyone wears glasses. That would be a hasty generalization. It would be an invalid argument. It's possible the premise is true and the conclusion is false. And so this should not be something we can prove with our proof method, with rules which are supposed to be truth preserving. Let's see what happens when we try it. So here's our conclusion. And the premise is Tanya wears glasses, TG. And sorry, I chose a name from the middle of the alphabet or a letter from the middle of the alphabet, despite the fact that I'm talking about a specific named individual and not an indefinite name. Okay, here we go. Let's say we just go line 2. Let's put AX, GX. And we'll cite it line 1, universal introduction, check proof. And it says, sorry, you can't do that. That's not a proper application of the rule universal derivation or universal introduction. And if you forget the rules or how they're supposed to look in the proof checker, there is a tab here called proof rules, and you can come back and check what it's supposed to look like and specifically what the constraints have to be. So this is any expression that has a name in it, and you can use the universal introduction rule where you cite just that line M, and the universal introduction rule where you put a little quantifier out front, the universal with the variable, and you replace all instances of C with the variable, whatever one you chose, in this case, X. The important thing is that X can't be in the expression or the statement you end on here. And that C, the name that's involved here, cannot appear in any open, unfinished proof, as in it can't be, this isn't really that clear, but what this means is it can't be in a premise or in an assumption, because you might look at a proof and you've been using C throughout it and the proof is open because it's not over. Specifically, C or whatever name you pick cannot be in a premise and it cannot be in an open assumption. And then when you wrap up and draw a conclusion that has the universal quantifier out front, you have to replace every occurrence of the name with the variable in question. So it'll remind you of what the rules are. So let's go back and do a different proof. We knew we weren't going to be able to prove that one anyway because it's an invalid argument. Let's prove this argument, and it should be clear that this one is valid because the premise says, given the same interpretation we've been using, everyone wears glasses, therefore everyone wears glasses. Now we know that these mean the same thing, but we'd still have to prove it using rules in our proof checker, because the proof rules don't say, well, as long as you can tell, then it's a valid step. It says use the rule to show that this series of symbols can be translated into these series of symbols using very specific, precise rules we know to be valid. Okay, let's put in our premise, and then the conclusion is the same thing, but with a different variable. First order. Okay, what do? We start by, let's just choose any object. If we know everything or everyone in the domain wears glasses, let A or P, or you're allowed to choose literally anything, any name. Let's just pick A. Doesn't matter. Except a variable. I don't think it'll let you pick a variable. Let's try it. Sometimes it helps to try and break things and see how they break so you understand how they work. Okay, let's go 1, A, E, and then well, it won't count it right because this won't be the conclusion. Let's just go this way. Let's pick Y, a variable. That was the only thing we were testing. And then let's go AX, G, Y, or no, let's do X. I was right the first time. We're treating it like a name. I hope it doesn't work. So if it does, then we just have to like remember more and the convention isn't super clear. Let's see. Okay, line 2 is not a proper application of the rule universal instantiation. And that's going to be because we picked an X. So you don't get to pick a variable name. You can pick a middle of the alphabet name. The book says you can't. The book says you have to pick a variable with a prime sign and also put a box around it. This one says you don't get to use any variables. You have to use a name. Doesn't matter which part of the alphabet that name comes from. Okay, so let's start over. Everyone wears glasses, so everyone wears glasses, but we're switching the variables around. New line, pick a name, any name. A. 1 AE. And now let's go, well, if a randomly chosen object wears glasses, A could have been any object chosen from the domain. And we know that object would have to wear glasses. Well, then we know every object would have to wear glasses, and let's choose any variable we want to express that. The rule says we can do that. 2. And this one's correct. So all of the little caveats or constraints have been followed in applying the rule. A hadn't been used in a premise or any open assumption, so it was free to be chosen. And now we get to generalize in this way. Okay, here is one we already did together. If you did not already do it in the proof checker, do it in the proof checker. And if you were feeling a little shaky, if you're not sure you'd be able to do it on your own without going back and looking at your notes, maybe try it again this time without looking at your notes as a hint and see if you can work your way through it now, especially if you didn't memorize it. And I assume you didn't memorize it, but if it feels like you memorized it, then maybe it's not that useful for you to do. But if you can not have memorized it, but kind of have a sense of how it's supposed to go and reason your way through it, it's worth doing. So pause and in your notes, reason your way through it, and then enter it into the proof checker and see if you can get the proof checker to check it out. If you succeed in doing all of that on your own, then feel free to skip the next part of the video and move to the next exercise. Otherwise, let's do it together. Putting a semicolon between premises. Making sure it's in first order mode. All right, I know I've got universals. I'm trying to get a universal. Within the scope, there are conditional statements, and I see what is sometimes called the pattern hypothetical syllogism, as in if C then M, and if M then W, then if C then W. So I know I'm going to want the conditional if C something then W something, basically what's in here. All right, so let's start by removing those quantifiers, and we have no reason to pick any name. So whatever we pick, it's random. It just has to be a name. And let's do that for line 2 again. If MA, then WA, and that's line 2, universal elimination. And now what? Sometimes I automatically hit new line, and then I realize like, oh, wait, I need to start a new subproof here because I've got these two conditionals, but I want this conditional. And whenever I want a conditional, I do a CP, unless like there's some other obvious way to get it. But usually if I want a conditional, I'm going to do a CP. So just erase the line. That's what that little X allows you to do. And instead start a subproof. And I'm just going to make the assumption the antecedent of the conditional I want, and in the proof checker, you don't have to justify your assumptions. Next line, let's do modus ponens on lines 3 and 5. That gets us MA, and we cite our lines as usual, but we don't get to write MP. You can either spell out modus ponens or write arrow elimination. Next line, modus ponens again on lines 4 and 6 gets us WA. 4 and 6, arrow elimination. And we did it. We have the antecedent of the conditional we want. We've shown that we can derive the consequent of the conditional we want. So we finish the subproof and add a line. If CA, then WA. We cite lines 5 through 7. And do we write CP? Let's check. The book calls conditional proof conditional derivation, and its shorthand is arrow introduction. Modus ponens is arrow elimination. CP proof is arrow introduction. You didn't have an arrow before, and now you've introduced it. Close. Last step is to introduce that quantifier, CA, horseshoe, WA. Oh wait, what do we do when we introduce the quantifier? We remove the names and replace them with the variable. Like that. And we go 8, universal introduction. And I'm allowed to do it because all along A was a name I picked for no reason whatsoever, could have been any name, and that is why it applies to everything. And so let's check our proof. This proof is correct. Take a picture of it. Let's do more examples. Again, I recommend you try it on your own, whether just getting straight away started with the proof checker or doing it by hand and then entering it into the proof checker. Even if you're pretty confident in what you did by hand, just practice using the proof checker, at least for these videos. So that way it's not something you're scared of later if you find you need to use it. Let's get started. What are we seeing? We have universally quantified statements. We want a universally quantified statement. Within the scope of those statements, I see a familiar pattern of reasoning. I see a disjunction, the negation of one disjunct, and the other disjunct. So I'm seeing disjunctive syllogism. So keeping that in mind, let's start a new proof. Don't forget to add in commas or semicolons as needed to separate the premises. All right, how do we start? Well, when you have universally quantified statements, a good place to start is just universal elimination. And we have no reason to introduce one name rather than another. So let's just pick A, CA, or DA. Line 1, AE. Line 2 will be not CA, 2AE. Now what? Well, now we neatly have disjunctive syllogism set up. So DA, that's lines 3 and 4. And we haven't done this one in the proof checker yet before. What do we call disjunctive syllogism? Oh yeah, the book calls it something longer, modus tollendo ponens, but luckily we're familiar with the acronym, DS. Okay, so now what? Well, we're awful close. We just introduce the universal quantifier. Are we allowed to do this? Yes, because A wasn't in any of our premises and it didn't show up in an assumption anywhere in the proof. So we introduced it. Could have been anything. That's why we get to conclude it must apply to everything. So we will cite line 5 and AI. Let's check our work. No errors yet, but you haven't reached the conclusion. Oh yeah, because I did make an error. And I said something that was grammatically okay, but is a weird thing to say. All things are such that A is a D. Like imagine C stands for I have a cat, has a cat, and D stands for has a dog. So this one says everyone has either a cat or a dog, and this one says everyone is such that they don't have a cat. In other words, no one has a cat. Everyone is such that they don't have a cat. Later in this lecture, we'll actually prove that not EXCX is logically equivalent to AX not CX. Everyone is such that they don't have a cat, i.e. no one has a cat. Therefore, everyone has a dog. It's kind of a weird thing to say that, like, everyone is such that A has a dog. That's weird. When you say everyone is such that, you're going to say something about each and every one of the individuals in the domain, not A. But okay, so that wasn't a case of, and I didn't want to do universal derivation. Oh wait, yeah, I did. Okay, check proof, done. And this is why the proof checker is neat. When you make just the stupid mistake where you really know how the rule works and then you just are going too quickly and you write down the wrong letter, but you totally knew the right answer. The proof checker will find those mistakes and you'll know them when you see them. Okay, let's do another example. This one's a little more complex. Just to make it a little more intuitive why this should be a valid argument, let's give an interpretation to our predicates and the one name. Let's let G be wears glasses, T refer to an individual in the domain, Tanya, and let's let S be looks smart. Premise 1 says, if someone wears glasses, then everyone wears glasses. Tanya wears glasses, line 2. And line 3 says, everyone who wears glasses looks smart. Each member of the domain is such that if they wear glasses, then they look smart. So everyone who wears glasses looks smart. Therefore, everyone looks smart. Okay, so does that make sense why that should be valid? One person, a named person, wears glasses. And this says if someone, at least one person wears glasses, hey, that was satisfied. Tanya is one person. So if someone wears glasses, and someone does, then it follows that everyone wears glasses. That's obviously not true, but if it's true, what follows? Okay, so then everyone wears glasses. And this one says everyone who wears glasses looks smart. Therefore, everyone looks smart. So maybe you can kind of see like it should be valid. And if you can convince yourself it should be valid, sometimes it kind of helps you to think about your proof strategy. Like knowing that one person wears glasses is on the way to showing that at least one person wears glasses. And so it looks like modus ponens is in view here. We can get from here to this statement. If this statement is true, this statement is true, which means we'll be able to use modus ponens to get this. And then we have two universally quantified statements, and inside the scope of those statements, it looks like another modus ponens. So I'm just seeing these patterns here. But let's say I don't see the patterns and I don't interpret this and see an argument that just makes sense. I can also fall back on my rules and paying attention to operators, the main operator, and or quantifier. So let's identify the main operator or quantifier in each of the sentences. What's the main operator and or quantifier here? Is it EX because it's first? No, this is a conditional statement whose antecedent is an existentially quantified state. So that's the main operator. This one's atomic. Atomic means no operators or quantifiers. This one, the universal out front, is the main quantifier, and this one here is. Okay, so what can I do? Well, because I have a universally quantified statement, I could just start with AE. I've got a claim about an individual, this one individual is a G, so I do know that I can use existential generalization. If you know something about a specific individual, then you know at least one individual has that thing, which also connects with the antecedent of this conditional. So it seems like I'm definitely going to want to use E introduction or universal generalization on this. And because the main operator is a horseshoe, the rules that apply are modus ponens or modus tollens. But it's going to be modus ponens because I see this relationship with the antecedent. So you can start here or you can start here. Now, one thing I'm thinking, if I don't see how the proof is going to go, T is already in a premise, and I know I'm going to have to use universal introduction at the end, and there's a constraint on when I can use it. I can't use it if T has been involved in my reasoning. So if I go GT, therefore ST by 3AE, and then later, this is part of my reasoning to get to this, I'm not going to be able to use universal introduction because it says you can't have T have occurred in a premise. We could check that this is true right now, but by trying to like put it in and showing that it won't work, but I promise it doesn't work. So I have some reservation about doing this, but at the same time, if I do this, it looks like I can do modus ponens, and that's something, and I could get ST, and ST looks like I'm on the road to here, right? So let's put, sorry, little t. Oh, accidentally hit caps. So let's do 2, 4. Let's actually just do it this way and see what happens. So that's modus ponens, or now, and then let's do A, X, I'll copy paste. By citing line 5. Let's put this in and see what happens. Okay, so I'm going to do universal elimination, modus ponens, universal introduction. New line, GT, horseshoe, ST, line 3AE, and that's a perfectly acceptable rule. The problem is we just shouldn't be able to use universal introduction at the end. Then lines 2 and 4 get us to ST. That's a perfectly good application of modus ponens. Let's see, what was I doing? Oh yeah, 2, 4 modus ponens. And then last step. Line 6 is not a proper application of this rule. Why? Because we got it from this line, which had a T in it, and a T was in a premise. So we can't make that step. So let's start over. We aren't going to go that route. Let's start instead with the insight that we can use existential introduction to get the antecedent and go from there. Okay, so Tanya wears glasses. From that, it follows that someone wears glasses. Lines 2 and E introduction. Now by modus ponens, lines 1 and 4, it follows that everyone wears glasses. Now, let's say we get stuck right here. One thing you might fall back on is, well, what things haven't we used yet? Sometimes things get used more than once, but we've already used this to get this, and then we use this with this to get this, but what we haven't used yet is this or this. So if we just highlight the stuff that hasn't been used yet, we might see some pattern or something. So I've got a bunch of universally quantified stuff. I want something universally quantified. I've got universally quantified things. And then inside the scope of those universally quantified things, it looks like modus ponens. So let's remove the universal quantifiers and do modus ponens. Okay, and I'm not going to pick T because it doesn't matter. At this point, I know that everyone wears glasses and everyone who wears glasses looks smart. So I don't care about this like having it be about T. So I want to pick any object. I know everyone wears glasses and everyone who wears glasses looks smart. So let's just pick any of those individuals that wear glasses. A, whoever, it doesn't matter which one we pick. That's why we get to use the universal introduction at the end. So this will be 5. And then GA, then SA from 3. And now I get to use modus ponens, SA, line 6, 7. And now we get to do the step where we do AX, SX. And that will be cite line 8. A didn't show up in a premise. So we get to make this step at the end. And we did replace all occurrences of A with the variable. All right, now we worked it out together. I did it on a screen. Maybe you did it with pen and paper. Put it in the proof checker and run it through. I'm not going to go through it and do it because every line needed is here with the exact justification, and this one does not require any subproofs. So it should be very simple to run through it and practice doing.